All right, so we're gonna work on chapter 11 today, which is our chapter on acids and bases. So let's look at a few of the definitions for acids and bases first. Okay, it's a good place to start. We want to be familiar with the terminology so that, we're on the same page when we're talking about, just some of the different terms that we're seeing in questions that we see in the reading. Uh, our first definition of an acid is going to be called an Arrhenius acid. Okay, and the definition for an Arrhenius acid is going to be any substance that produces hydrogen ions, which are our H plus ions when they dissolve in water. So, for example, when you take some HCl and you dissolve it in water and you end up with H plus and Cl minus, the formation of that H plus means that HCl is going to be an Arrhenius acid. Arrhenius acids are also considered electrolytes because they produce hydrogen ions in water. And anything that produces ions in water is going to be able to act as an electrolyte. It's going to be able to conduct that electric current. Your acids are going to have sour tastes to them. Okay. You'll notice that if you ever look on like the packaging of any of like the sour candy and stuff that you see, you'll see a lot of acid components in there to give it that sour taste. Your Arrhenius acids or acids in general will turn blue litmus paper red. Litmus paper is a type of paper that can tell you whether something is acidic or basic based on color changes. So if you have blue litmus paper and you put it into something that's acidic, that blue paper will turn a red color. If it's not acidic, then the blue paper will just stay blue. Um, Acids also are going to be able to corrode metal. Okay, that's another property of them. For our Arrhenius bases, we're going to be focused on a different component that's produced. We have hydroxide ions that are going to be produced. So our Arrhenius bases are anything that would produce a hydroxide ion when it's in water. All right. Um, your bases are going to taste bitter or they'll taste chalky. Bases are also going to be electrolytes because we're producing those hydroxide ions, and anything that produces ions is an electrolyte. Your bases are going to feel soapy or slippery. And when you're looking at litmus paper, um, instead of, let's see, and when you have blue litmus paper and it turns red, that's going to tell you that something is acidic. If you have red litmus paper that you start with and you put it into a solution, and then that red litmus paper turns blue, then you know that the solution is basic. Okay. Um, you can also use what's called a phenolphthalein indicator in a solution to tell if it's basic, because your phenolphthalein indicator will actually turn from clear to a pink color if it's put into a basic solution. Okay. Um, so when you have Arrhenius acids, you're going to be producing H plus ions. When you have Arrhenius bases, you're going to be producing OH minus ions. And that's going to be the biggest distinction between acids and bases that you first have to be comfortable recognizing. Acids are going to be associated with that H plus ion, and bases are going to be associated with this OH minus ion. So here's a breakdown of that. Okay, your acids and your bases. In your acidic solution, you see you have the H pluses floating around. You also have the Cl minus ions, but those are not going to have an impact on whether something is acidic or basic. It's just the H plus ions that make something acidic. And on the other hand, on the other side of that, the OH minus ions in this solution are what makes the solution basic. The Na plus ions don't contribute to, to the basic nature of the solution. Okay, and there's your recap of the characteristics of your acids and bases you can refer to. Now we want to talk about how we give acids their names. There are two types of acids, and we have two different ways to name acids depending on which category they fall into. So we're going to have what are called binary acids, and these are going to be acids that do not have any oxygen in them. Okay. It's going to be a hydrogen cation and one other anion attached to the hydrogen, but that anion that's attached will not contain oxygen. And then we're going to have oxyacids, and these are going to have hydrogen as the cation, and attached will be a polyatomic ion that's going to contain oxygen. Okay, so when you look at the formula for your acid, you have to place it into one of these two categories before you can give it a name because they're named slightly different ways. For our binary acids and for our binary acids only, we're going to write a hydro prefix at the start of the name. And then we're going to follow that hydro prefix with the nonmetal's base name, just like we did when we were naming compounds, when we were naming anions at the beginning of the semester. After we write down the nonmetal's base name or the anion's base name, we're going to add an IC ending, and then we're going to write the word acid afterwards. So for example, and I'm sure we're going to have an example shortly, but just so that you could see what I'm talking about here. We said that HCl was an Arrhenius acid. When you look at HCl, you know that it's a binary acid because there's a hydrogen in the front and there's no oxygen that follows it. So now to name it, going based on those 4 steps that we just wrote down, step 1, we write the hydro prefix. Step 2, we follow that hydro prefix with the base name of our nonmetal. So that's chlorine. So I'll write the base name, which is chlor. Step 3, we're going to add the IC ending. And then step 4, we're going to add the word acid. So HCl is going to be hydrochloric acid. Okay. If we have HBr, this is going to work the same way. We recognize that it's a binary acid. And so the first thing we do is write the hydro prefix. We recognize that that's bromine. So we write the base name of the anion. Then we add the IC ending and then the word acid, hydrobromic acid. Okay. Let's see how that changes when we have our oxyacids. So when you have your oxyacids, you're going to recognize that you have an oxyacid because you'll have your hydrogen ion to start with, and it will be followed by a polyatomic ion, and that polyatomic ion is going to have oxygen in it. Okay. I'm going to write down 2 examples for us to look at once we talk through these rules. So if the polyatomic ion that creates your acid is a polyatomic ion that ends with ATE, then you're going to remove the ATE ending and you're going to change that ending to IC. And that's going to be the name of your acid. If the polyatomic ion ends in ITE, then you're going to remove the ITE ending and change that ending to OUS. Okay. And then you'll follow with the word acid at the very end of all the names. You're going to notice that when you're naming oxyacids, you do not include the hydro prefix. So that first step that we took in our naming of binary acids is not included here. You do not use the hydro prefix when you name oxyacids. You name the oxyacids directly from the name of the polyatomic ion that has created the oxyacid. Okay, so for these 2 examples here, when I look at HNO3, I'm going to recognize, first of all, it starts with an H, so I know it's going to be an acid. And when I look at the NO3, I know that this is going to be the nitrate ion. Okay. I see that the nitrate ion ends in ATE, and I'm going to remove that ATE and I'm going to replace it with an IC. And then I'm going to replace the word ion with the word acid. So now the name of this acid is just going to be nitric acid. There's no hydro in front. It's just nitric acid. If I have HNO2, which looks very similar, again, I recognize there's a hydrogen out front. I know it's an acid. Now I focus on the NO2, and I know that this is going to be the nitrite ion. This is why it's so important to have those polyatomic ions memorized, because then when you're looking at the names of compounds later on, you're going to be able to know their names and recognize them. So this is the nitrite ion. I'm going to focus on that ITE ending. I'm going to get rid of it, and I'm going to change it to OUS. And then I'm going to take the word ion and replace it with acid. So this is going to be nitrous acid. So our ATE ending goes to IC, and our ITE ending goes to OUS when you have oxyacids. Okay. Let's look at this example slide, which just kind of reiterates what we just did, but now we can look at them side by side. So we have our HCl here, which is our binary acid. So when we name this, we start with the hydro prefix, then the chlor, then the IC ending, and then acid, hydrochloric acid. And then when we have our oxyacids, acids that have, you know, the oxygens in the polyatomic ion. Sorry, lost my train of thought there. If you have HClO3 or HClO2, you're going to recognize that for the ClO3 minus, that's the chloride ion. And so if you have HClO3, that ATE ending is going to change to IC. So you'll have chloric acid. For HClO2, you'd recognize that the ClO2 minus is going to be the chloride ion. And so that ITE ending changes to OUS. So you're going to have chlorous acid. Okay. So our summaries, when you're writing names, when the name ends in acid in general, your formula is going to start with an H. Sorry, this is like the reverse, writing formulas for your acids from the names. When the name ends in acid, you know that you're working with an acid, and so you know that your formula is going to always start with an H when you have an acid. If you see hydro in the name that you're working with, then you know that there will not be oxygen in your formula. Okay. If you have an acid that does not have hydro in its name, then you know it will be an oxyacid. It has to be. If the ending of your oxyacid ends in IC, it's going to be a polyatomic ion that ends in ATE. So it's just the reverse logic of what we just did. If the ending of your acid is OUS, then the polyatomic ion that it came from ends in ITE. And you'll be able to work backwards to create the formulas for that. Okay. So we're going to look at some examples on the next few slides, and we'll work kind of both ways from this. I think actually before I do these examples, we'll do 2 examples of this process. So let's work with, stop share a minute. All right, so if I have, I'm going to do phosphoric acid, sulfurous acid, and hydrocyanic acid. Okay, I want to write the formulas for all three of these things. Start out with the hydrocyanic acid. It's going to be my only acid that starts with hydro. So I know that this is not going to contain oxygen. This is a binary acid. Okay. So I have to look here and say what anion has the base name cyan. And if I remember from my polyatomic ion table, cyan is going to be the base name for the cyanide ion. All right. And once you know the ion that is being referred to in your formula, then you can write out the formula for your ion. So cyanide ion is going to be Cn minus 1. And whatever the charge is on your anion, that's how many hydrogens go in front of your neutral acid formula. So I have a -1 charge here. So my formula for hydrocyanic acid is going to be 1 hydrogen and then the Cn after it. Okay. For sulfurous acid, I know that I'm going to be working with a polyatomic ion that contains oxygen. When I look at my list, I'm going to be looking for my polyatomic ions that end in ITE because I have an OUS ending here. Okay. And the polyatomic ion that this is going to refer to is going to be my sulfite ion. Okay. ITE, OUS. My sulfite ion has a formula of SO3 with a -2 charge. That tells me that I'm going to need 2 hydrogens in front of the SO3 to make my neutral formula because each hydrogen is a H+1. So my formula for sulfurous acid is going to be H2 SO3. Okay. For the last example up here, I've got an oxy acid that ends in IC. So I know my polyatomic ion is going to end in ATE. This is going to be my phosphate ion. Okay. And my phosphate ion has a formula of PO4 with a -3 charge, which means I'm going to need 3 hydrogens in the front to balance it out. So my formula for phosphoric acid is going to be H3PO4. Okay, so that's how we're going to go from the names to the formulas. But now we're going to practice. We'll do a bunch of different practice. We'll do some formulas and then turn them into names, and then some names and turn them into formulas. So we're starting with naming HI, naming HF, and we already named HBr, so we don't have to do that one again. Okay, so here we know that both of these are binary acids because there's no oxygen. And so we're going to start with our hydro prefix. Then we're looking at our anion. This is iodine. So we're going to write the base name for our anion. Then we're going to add an IC. And then the word acid. Hydroiodic acid. And then for HF, we're going to start with the word hydro. This is fluorine. So we're going to write the base name for fluorine. Then we're going to add the IC and the word acid. Hydrofluoric acid. On the following slide, they're asking us to name some oxyacids instead. And we know that they're oxyacids because they're all going to have oxygen in them. So they're asking us to name HC2H3O2, And we already did these ones. We did HNO2 and HNO3 already. Let's do, I'm just going to change up the examples a little bit. Let's do HClO and HClO4. Okay. And again, I mean, I would recommend like trying to do these on your own. Okay. All right. So once we recognize that it's an oxyacid, we know that we're not going to start with the hydro prefix. We're just going to look at the polyatomic ion and we're going to recognize the polyatomic ion's name. So this is the acetate ion. Okay. And so I see that the acetate ion ends in ATE. So I'm going to rewrite it with its IC ending. So this is going to be acetic acid. Okay. For our HClO, I am going to look at the ClO here, and I'm gonna gotta think to yourself, what is the ion that's going to be ClO minus? That is going to be our hypochlorite ion. Okay. Then we're going to take that ITE ending, get rid of that, and change it to an OUS. So the name of this is going to be hypochlorous acid. Okay. And then for the last one, these two look very similar, but the name of this ion is different. When you add those extra oxygens, it changes the name of this ion. So this is going to be the perchlorate ion. Okay. And that ATE ending is going to change to an IC. This is going to be perchloric acid. Okay. The next two examples ask us to write the formulas from the names. One of them was a perchloric, so I'll change that example. So let's find the formula for well, we'll write the number 4 down here. So we'll find the formula for carbonic acid. And we'll find the formula for chloric acid. Okay. So for our carbonic acid, you focus here and you can talk yourself through this. Like you don't have to know it right away, but sometimes as you're writing it out, like going through step by step helps you like piece together what exactly is going on. When you look at the word carbonic acid, you can take that word carbonic and you can literally rewrite the word. So take the carbon and change the IC into ATE. So this is going to be the carbonate ion. And then once you write down the carbonate ion, it's going to be easy to find the carbonate ion. It's CO3 with a -2 charge. And once you see the formula for it, then you look at the charge, however many negative charges it has, that's how many hydrogens go in the front. So our formula for carbonic acid is going to be H2CO3. For chloric acid, again, we look at the IC ending and we know that this is going to be the chlorate ion. And we're going to know that the chlorate ion has a formula of ClO3 with a -1 charge. So there's going to be 1 hydrogen in the front of it. So the formula is going to be HClO3. when we look at naming bases instead of acids, we're going to see that there's not really much new for us to learn here, because naming our bases is just naming our ionic compounds that contain hydroxides. So you name the metal first, and then you name the hydroxide ion after it. Just like any typical ionic compound. So barium hydroxide, aluminum hydroxide, you name the metal first, you name the hydroxide second. And because it's an ionic compound, you do not use prefixes as part of the names. So we have a few more examples here. Definitely take some time. Okay. We can go step by step here and try to use some kind of like logic when we're looking at these. So right away, we should know, based on the hydrogens that are in the front, that these are going to be our acids. So we can underline things with the word acid. And pick a different color. For these OH minuses, these are going to be our bases. So these are going to be our hydroxides. Okay, now it's just going to be about matching up the right ones. So this is calcium, this is hydroxide. So that's the name, calcium hydroxide. This is sodium, this is a hydroxide. So this is going to be sodium hydroxide. For our acids, okay, we're going to be recognizing the polyatomic ions. The NO2 is the nitrite ion. And if we change the ITE ending to OUS, this is going to be nitrous acid. With our H2SO4, we have the SO4 polyatomic ion, the sulfate ion. We're going to change that ATE ending to IC. So this is going to be sulfuric acid. And then for HIO3, this is the iodate ion, one of our oxyanions. If we change that ATE ending to IC, it's iodic acid. Okay, so you can use process of elimination for a lot of these. You just got to go one step at a time. And it's just about recognizing, first of all, whether it's an acid or a base, and then recognizing the name of the ions that are attached. Let's look at the characteristics of acids or bases. Our little pen out again. If it has a sour taste, that is going to be a property of an acid. If it produces OH minus ions in aqueous solution, that is absolutely going to be a property of a base. If it has a chalky taste, that is also going to be the property of a base. If it's an electrolyte, that can be a property of either one of those. And if it produces H plus ions in aqueous solution, that's absolutely a property of an acid. Okay. Sour taste and hydrogen ions, those are properties of acids. Hydroxide ions and a chalky taste, those are properties of bases. And both acids and bases can act like electrolytes, which we actually saw in lab. Our second acid-base theory that we want to look at is called the Bronsted-Lowry acid-base theory. And the way that your acids and bases are defined is going to be a little bit different in the Bronsted-Lowry theory versus the Arrhenius theory. Arrhenius just says that something has to produce hydrogen ions in solution, and a base is something that just has to produce hydroxide ions in solution. With your Bronsted-Lowry theory, the definition is going to involve protons, H plus ions. And an acid is going to be defined as something that can donate an H plus ion. A base is going to be defined as something that can accept an H plus ion. So let's look at what we mean by donate versus accept here. Okay, so in our starting reactant side over here, we have HCl and we have H2O. When these two things react, the HCl is going to donate its H plus to the H2O, and the H2O is going to accept that H plus. Okay. So now on the product side, your H2O has turned into H3O plus, and your HCl has turned into Cl minus. So the HCl was a proton donor, an H plus donor. And so it's going to be considered the acid in this case. The H2O is the proton acceptor or the H plus acceptor. And so it's going to be considered the base. Okay. Um, let's look at what happens when we put something like NH3 into water, because we're going to watch actually water here. Water is one of the few substances that's able to act as an acid or a base in solution, depending on the solution that it's in, depending on what you mix the water with. So in this case, we mix water with ammonia with NH3. Instead of accepting a proton, the water is going to actually give away one of its H plus ions to the NH3. And now on the product side, we have NH4 plus. So in this scenario, our acid was the H plus donor. So our water was the H plus donor. So our water is acting as an acid. And our NH3 was the H plus acceptor. So it's acting as a base. Okay. So just depending on what it's mixed with, the hydrogen ion can either pick up an H plus ion or it can donate an H plus ion. There's a special name for the reactant and product pair that's part of an acid-base reaction like this. We're going to see that when we have our acid on our reactant side, after it loses its proton, its H plus, on the product side, it's going to be missing its proton, right? But these two things, they're linked to each other because this is what it started as, and this is what it ended as. And that pair of substances, the starting substance and the ending substance, this is called a conjugate acid-base pair. Okay, so this is your acid, and this is the conjugate base that it forms on the product side. The other reactant that you have, right? If you start with an acid, one thing is an acid, the other thing has to be a base in an acid-base reaction. So when your base picks up the H plus ion, it's going to be a little more positive on the product side because it just picked up an H plus. So this is going to be another pair. This is going to be your base and your conjugate acid pair. Okay, there's always going to be one thing on the reactant side that's connected to one thing on your product side. The other thing on your reactant side will be connected to the other thing on your product side. All right. Each of these pairs is going to be related by the loss and the gain of a hydrogen ion. So you'll be able to look at each component and you'll be able to pick out the acid-base pair, the two things that are linked together, because they'll be different from each other by just one H plus ion. So look at this reaction here. We have HF plus H2O. And what happens with the HF is that it's going to donate its proton to the H2O. That's what's happening here. So in terms of the pair that's forming, our HF turns into F minus, because it loses that proton. So the pair is the starting reactant and then the thing that it turns into on the product side. And for our H2O, which is our base, it started as H2O and it ended as H3O plus. So it started out as a base and then it ended as a conjugate acid. Our HF started as an acid and it ends as a conjugate base. All right. But you'll notice that each of those things that we're calling a pair here, the difference between HF and F minus is one H plus ion. The difference between H2O and H3O plus is one H plus ion. We want to be able to recognize conjugate acid base pairs, and we want to be able to recognize the conjugate acids and bases of particular compounds. So when you're looking at that NH3 and water reaction that we had, let me sketch this. I'm going to sketch the reaction out here so that what they're saying on this slide makes a little more sense. Okay. So we have two different pairs here. We're going to have the NH3 to NH4, all right? That's going to be one acid base pair. The second acid base pair is going to be here. H2O and OH minus. Notice that each of these things that are paired up are different based on one hydrogen ion. So for NH3 to become NH4 plus, we're going to add a proton. And then it's going to become NH4 plus. So this is going to be the base. And if we add a proton, this is going to be the conjugate acid. Okay. For our other one, we have H2O. And for H2O to become OH minus, it has to lose a proton. It has to lose an H plus. And when something loses an H plus, that means that it starts as an acid. And if it loses an H plus, it forms the conjugate base. Okay. And any acid-base reaction is going to have one base that turns into a conjugate acid and one acid that turns into a conjugate base. All right. Okay, so they're asking us in the next learning check. I'll put this up here just for visual. And then we'll look at this on the board. It's asking us to identify the Bronsted-Lowry acid base and conjugates in the following reactions. So definitely take a second and try this out. See if you're understanding the different definitions. Okay, we'll start here. First of all, we can connect the things that are linked to each other. So you see you have the HNO3 and the NO3. You see the similarities are with the NO3s. So we know that these two things are going to be a pair. Okay. And then we can ask ourselves, for HNO3 to turn into NO3 minus, what happened to it? Did it gain a proton or did it lose a proton? And clearly it has the H here and it doesn't have it here. So it lost a proton. It donated an H plus. And when something donates an H plus, that's going to be the definition of an acid. If this is an acid, then its pair is going to be a conjugate base. Okay. Now over here, we have our H2O and our H3O plus, and these two things are going to be linked to each other. And when you ask yourself, well, how did H2O turn into H3O plus? What did it gain or lose? And it accepted an H plus. It gained an H plus for it to turn into H3O plus from H2O. So for something to accept an H plus, it has to start out as a base. So our H2O is going to be a base. And then our H3O plus is going to be the conjugate acid. Okay. So this is going to be acid, conjugate base, base, conjugate acid. Those are our pairs for our first reaction. For our second reaction, we have hydrofluoric acid and water. Okay. And again, we can start off by looking at what's linked to each other. Our HF and our F minus are going to be linked because they both have the fluorine in them. And the difference between HF and F minus is that HF had to donate a proton. It donated or it lost an H plus, and that's how it became F minus. So our HF is an acid, and our F minus is going to be the conjugate base of that acid. Okay. The difference between H2O and H3O plus is that H2O gained a proton when it became H3O plus. So if the H2O is able to accept a proton, then the H2O is going to be a base in this case, and the H3O plus is going to be its conjugate acid. Okay, we're going to look at the next example here. We're looking, it's the same type of question in this case, but we're just working with a different reaction. This reaction has no water in it, so we're going to be looking, just doing the same process, really. We're just looking at different substances. We're going to look and we're going to see which pairs of reactants and products are linked to each other. And we're going to be keeping track of whether they gained or lost a proton. Okay. So I see that my HNO3 and my NO3 minus are linked to each other. And my NH3 and my NH4 plus are linked to each other. Those are the links that I can see. And so when I'm looking, start the HNO3, for HNO3 to become NO3 minus, it lost an H plus. So this is going to be my acid. For NH3 to become NH4 plus, it gained a proton. So my NH3 is going to be a base. If my HNO3 is an acid, then my NO3 minus is going to be its conjugate base. And if my NH3 is a base, then my NH4 plus is going to be its conjugate acid. Notice how your acid and your base are on your reactant side, and both of the conjugates are on the product side. Okay. So you're always going to find the conjugate to your reactant on the product side of the reaction. Okay, for our next set of examples, they are asking us to find conjugates of these things. Let's share this first, and then we'll write down how to work this out. They're asking us to find the conjugate base for the first set of questions. And then they're asking us to find the conjugate acid for the second set. And you have to, think about what we've been talking about when you're thinking about each of these definitions. When you're finding the conjugate base of an acid, for an acid to turn into its conjugate base, the acid has to lose a proton. So to find the conjugate base, we're going to remove a proton from the formula we're given. Right? That's how we're going to connect the acid to its conjugate base. If we're going to find the conjugate acid of a base, we know that bases are going to accept protons to become the conjugate acids. So if I want to find the conjugate acid for any formula that I'm given, I'm going to add an H plus to the formula that I'm given. And that will tell me what the conjugate acid formula is. Okay. So finding the conjugate base of something means I'm removing an H plus from my original formula. Finding the conjugate acid of something means that I'm going to be adding a proton to the formula. And remember, by the word proton, I mean one single H plus. Okay, each H plus is one proton. So for our first batch, we have HBr, H2S, and H2CO3. And for each of these, I'm removing one hydrogen and one positive charge. It can't just be one, it has to be both. So if I remove a hydrogen and a positive charge from my HBr, I'm going to be left with Br minus 1. Okay, I removed the hydrogen and it went from neutral to minus 1. Here I have H2S. I'm going to remove one hydrogen and one positive charge. So I'm going to have HS minus 1. For H2CO3, again, I'm removing one hydrogen and one positive charge. So I'm going to have HCO3 minus 1. On our other side, when we are going to be finding our conjugate acids, I'm going to add my H plus to the formula that we're given to start with. So we're starting with NO2 minus. We're starting with NH3 and OH minus. Okay, so I'm adding one hydrogen and one positive charge to each of these. So if I add a hydrogen and a positive charge to my first one, I'm going to have HNO2, no charge, because the plus one and the minus one cancel each other out. For NH3, I'm adding a hydrogen, so I'll have an H4, and I'm adding a positive charge. So I'm going to have NH4 plus 1. For OH minus, I'm going to have one oxygen and two hydrogens. And +1, -1, no charge there. And you'd write it out as, you wouldn't write it out as OH2, you'd write it out as H2O. Okay. Let's look at the next question, which is linked to this one, because in this question, they're giving us these sets and they're asking us to identify the things that are conjugate acid-base pairs. For something to be a conjugate acid-base pair, their formulas can only be different by one single proton. That's it, only one proton. So if they look similar, but they're differing by more than one proton, then they cannot be an acid-base pair. Okay. So when we look at the first one, we have HNO2 and we have NO2 minus. So the difference between this and this is the HNO2 lost one proton and it became NO2 minus. So this is a good acid-base pair, conjugate acid-base pair. Here we have H2CO3, and there should be a comma here. And then we have CO3, 2 minus. So the difference between these two formulas is that our H2CO3 lost 2 H's and it lost 2 positive charges. So even though these formulas look similar to each other, these are not a conjugate acid-base pair because conjugate acid-base pairs only differ by one proton. Okay. When we have HCl and then ClO4 minus, these are two completely different anions. Cl minus and ClO4 minus are two totally different things. So that's not going to be an acid-base conjugate pair. When we have HS minus, and we're looking at H2S, the difference between these two things is HS minus has one proton added to it, and then it becomes H2S. So that is a good acid-base pair. And then we have NH3 and NH4 plus. The difference between those is that the NH3 has one proton added to it. So that's also a good pair. Okay, so when we're looking at conjugate acid-base pairs, we're looking for things that differ by exactly one proton between them. This is a good term to look at next. Now we've seen water a few times in different reactions, and sometimes water is acting like an acid. Sometimes water is acting as a base. There's a name for that. It's a name that you have to know. It's called being amphoteric or amphiprotic. Both of these words are close enough in definition. They imply the same thing. It's something that can act like an acid or a base, something that can donate a proton or accept a proton, depending on what it's mixed with. Water donates an H plus when it's reacting with a stronger base. Water can accept an H plus when it's reacting with a stronger acid. So anything that can act as both an acid or a base is going to be considered amphoteric or amphiprotic. Now let's look at acid-base strength and what that means for our solutions. Two terms, strong acid and weak acid, that can sometimes be confusing because of what they imply. When you call something a strong acid, what you are saying is that acid is going to ionize completely in solution. Okay. And we've talked about this before when we were talking about electrolytes. Strong acids are strong electrolytes for that reason, because they're going to completely ionize in solution. Your weak acids are only going to separate partially, slightly. They're only going to form a few ions in aqueous solution, and the rest of the solution, they'll stay in their molecular form. Okay. Just because an acid is classified as a weak acid, though, doesn't mean that it is not physically dangerous. caustic. It just means that it's not going to completely dissociate. That's the only thing that the designation of weak acid means. You just don't want to get that part confused. And just because something is a weak acid doesn't mean that it couldn't potentially like burn your skin or something like that. So when we have strong acids, what we would see in solution is that if you start out with a strong acid, then once you put it into solution, 100% of it is going to separate and turn into its ion form. You're going to have huge concentrations of both the cation and the anion that is present. For your weak acids, whatever your molecular formula is that you're starting with, so here we have HF, when you mix it with water, on the product side, you'll still have your molecular acid in large quantities, but you'll have a very tiny amount of ions that are forming. Okay. The concentration of H plus and your anion are going to be very, very small. This is just repeating what we just said here. So examples of a strong acid is something like HCl, which will completely dissociate into H plus and Cl minus. An example of a weak acid is something like acetic acid, which is going to mostly contain acetic acid when it dissolves, but there'll be a few H plus ions and a few acetate ions that are floating around in solution as well. Okay. Another type of acid, well, and that's not another type of acid, but another notation that we want to be familiar with for acids are has to do with the number of hydrogens that are out in the front of their formula. So you'll notice that for H2CO3, there's 2 hydrogens out in the front. So what that means is that the acid has the potential to release 2 hydrogen ions or 2 protons into solution, even if it does it in 2 pieces. So let's say that the H2CO3 reacts with water and it forms HCO3 minus 1. That HCO3 minus 1 can also react with water and form CO3 2 minus. So if we start out with H2CO3 and we end with CO3 2 minus, that means that we've released 2 H plus ions into solution. And remember that H plus ions are also called protons. And so if you have an acid that starts out with 2 hydrogens in the front, that type of acid is called a diprotic acid because you can release 2 protons into solution when it separates. Okay. Any acid that has the subscript of 2 next to its hydrogen in the front is going to be considered diprotic. This is only true for the hydrogen that's at the front of your formula. So when you have something that has multiple hydrogens in the middle of the formula somewhere, that's not going to count for this. Okay. Something else, another acid that is considered a diprotic acid is sulfuric acid, H2SO4, because when H2SO4 is completely finished separating, it will have released 2 hydrogens into the solution. Okay, even though it happens in a 2-step process, the H2SO4 is going to separate into H3O plus, which is another way to write down our proton, and HSO4 minus, and then that HSO4 minus will continue to react with water, will release another proton, and will end up as SO4 2 minus. So we start out as H2SO4, and we end all the way at the end as SO4 2 minus. So that means that 2 protons were able to be released over the course of that process. Our strong bases, just like our strong acids rather, are also going to be strong electrolytes. Our strong bases are going to be formed by our metals that are in group 1 and group 2 that are combined with our hydroxides. Okay. Our strong bases are going to completely separate in water just like our strong acids do. Our weak bases are things, a lot of them contain nitrogen, you'll see, but they're things that they don't fully ionize. They accept hydrogen ions, but not not at a really high rate. So they say that they're poor acceptors of hydrogen ions, and that's because not every ammonia that you put in water is going to accept the hydrogen ion. Only a few of the ammonias that you put in water are going to accept the hydrogen ions and form ammonium ions from it. Okay, for example, it works the way that your weak acids do. Like when you put your weak acid in water, not all of it separates. So when you have a weak base, if you put your weak base in water, not all of the weak bases are going to accept that hydrogen. Some of them are just going to just stay as they were. And so you don't end up making ions if your weak base doesn't accept the H plus ion. Which means that you end up with a lot fewer ions in solution. And if you have fewer ions, then you're going to have a weaker electrolyte. One common example of a weak base is your ammonia. That's the biggest example that we keep on showing you with these. So when your NH3 and your H2O react, notice the double arrows here, because some of that NH3 will accept a proton and become NH4 plus, leaving behind OH minus. But most of it's going to just stay as NH3. Now, we can figure out the direction of our reaction, the direction of our separations, of our ion formation, based on the strength of our acid or our base. Okay? Strong acids are going to have very weak conjugate bases, and those conjugate bases will not want to accept hydrogen ions and reform into their original compounds. Because strong acids want to, they're very good at staying separated and making your solutions acidic. We're going to see that there's going to be a relationship between the strength of your acid and the strength of a conjugate base that it forms. As your acid strength decreases, so as your acid gets weaker and weaker, that acid's conjugate base will get stronger and stronger. And the opposite is true too. When you have a base that's very strong, its conjugate acid will be very weak. But as your base gets weaker, its conjugate acid gets stronger and stronger. In any acid-base reaction, there's going to be, it says 2 acids and 2 bases here, but it's just like we saw before. There's going to be an acid and a conjugate base, and a base and a conjugate acid. So technically there's 2 acids and 2 bases. They'll be, separated on each side. On each side, one acid is going to be stronger than the other, and one base will be stronger than the other. Okay, so if you have a strong acid on your left side, you're going to have a very weak conjugate base on your right side. If you have a very weak base on your reactant side, you'll have a very strong conjugate acid on your product side. That's how that's going to work. But you can compare your acids and your bases and the strength of them to figure out which way your reaction is likely to proceed. When you're looking at your at a list of acids and bases like this, you do need to be able to determine, just based on the formulas, which acids are strong or weak. These are things that you have to have memorized. You have your list of strong acids and strong bases from your chapter. You have to know those, okay? So I would recommend going through and you just have to remember the strong things, the strong acids and the strong bases, and there aren't many of them. If you know the strong acids and the strong bases, then you'll know that anything that's not on that short list that you've memorized would be considered weak. So our strong ones in this case are HBr, that's a strong acid, NaOH, strong base, H2SO4, strong acid. The other things on this list, that's going to be a weak acid, weak base. We know that this is base because it's OH, OH, and the H's out in the front tell us that the other ones are acids. When you are looking at a table like this one, you can identify the stronger pairs, the stronger acid or the stronger base within each pair, like they've given us here. Just based on the list here. So they've given us like HNO2 and H2S. So we can find these on we have HNO2 here, we have H2S down here. So our HNO2 is going to be the stronger acid in this case. HCO3 minus versus HBr. HBr is a strong acid, so we didn't even have to look at that. And then H3PO4 versus H3O plus. H3O plus is the definition of the acid ion. So this is gonna be the strong one here. So here, here, and here. Two of these you would not need this table for. For them to ask you this question for part B and part C, you would not need the table for this. When you look at H3O minus versus HBr, you should just be able to know that this is a strong acid. Okay. And then you're going to have H3PO4 and H3O plus. Your H3PO4 is down here in your weak acid section, right? And your hydronium ions up here. So, but you'll notice that all these that are listed up here, these are your strong acids. All right. All right, we're going to look at the weak acids and weak bases next. All right, so you're going to see the title of this says dissociation of weak acids and bases. And that's because since weak acids and weak bases don't completely separate, we have to be able to figure out how much they're going to separate in solution. And we're going to have to write out these equilibrium reactions that represent how our weak acids and our weak bases behave in water. Okay, so you're going to see that this looks real familiar to what we saw with our equilibrium reactions and our equilibrium constant expressions. So we're going to see that every weak acid, when we add it to water, there's going to be like a little reaction that occurs here. And on our product side, you'll see that the hydrogen from your acid is going to move on to the oxygen of your H2O. It's going to form your H3O plus, and it's going to leave behind your product, your CHO2 minus. Okay. This is just an example of a weak acid reaction, but every weak acid reaction is going to kind of do the same thing. Now, what we just described is the forward direction of the reaction. And for all of your weak acids, that forward direction is going to be pretty small. What's more common is that your H3O plus and your CHO2 minus reform themselves into your HCO2, HCHO2 rather. And that's also going to be true of most of your weak acids, is that your original molecule is going to be more prevalent than the different ions that are formed when they separate. So we can take the reaction that we just looked at and we can write it out We see that double arrow there, so we know that it's in equilibrium. It's an equilibrium reaction. And when we write out our equilibrium reaction as an equilibrium constant expression, a K expression, we're going to call this expression the Ka, which is going to stand for acid. So it's an equilibrium constant for our acids. Okay. This is also called an acid dissociation constant because our acid is separating or dissociating. All right. Just like with our other K value, when we look at our reaction here, it's going to be our products divided by our reactant raised to the coefficients. And just like in our other equilibrium constants that we mentioned, we're not going to include our pure liquid in this reaction, right? Remember, we leave our pure liquids and our pure solids out of our equilibrium constant expressions. So when we write our equilibrium, our acid dissociation expression for this, it's going to be H3O plus times CHO2 minus divided by HCHO2. And that equilibrium constant dissociation for your formic acid is 1.8 times 10 to the -4. And remember what we said about K values that are really small. It means they favor the reverse direction. So it's not surprising to us that if you took some formic acid and dissolved it in water, you added it to water, and then you took the concentration values of all of the components that are in that solution, that most of what would be present would be your HCHO2 in its molecular form. Okay, and that's just, I mean, you could tell that from the size of the acid dissociation constant. And it makes sense because it's a weak acid. So we would expect that it's not going to be separating out to a great deal, right? When your Ka values are very small, the equilibrium is going to lie to the left towards your reactants, meaning you're not going to make much product. When your Ka value is very large, the equilibrium would be towards the right, favoring the products. Your weak acids will all have small Ka values. So they're all going to lie to the left on that equilibrium scale. So they're all going to favor your reactants. Your strong acids are going to have Ka values that are very large. They're so large that we're not going to have to worry about calculating them. They're all going to favor the production of products, right? Because strong acids are going to have 100% dissociation. We're going to be able to make a base dissociation constant called Kb, which works the same way as Ka does, but this will be for bases instead. When our Kb value is a small number, then again, our equilibrium is going to favor the reactants, meaning that not very much hydroxide ion will form. Our base is going to stay in its molecular form. When our Kb values are very large, that's when our equilibrium would lie towards the right and we would make a lot of product. But that will not be true for any weak base. So you see for our reaction here, the Kb expression is going to be our products, the CH3NH3 plus times OH minus divided by our CH3NH2. And we leave out the water because it's a pure liquid. Okay, so here's are just some examples of weak acids and weak bases and their corresponding dissociation constants. And you'll see for all of our weak acids and weak bases, the exponents on these are all very tiny exponents because they're all weak. So they're not going to have a very large amount of separation. Okay. So when we're looking at acid strength, acid or base strength versus the equilibrium position, when we have very strong acids, our equilibrium position is going to be towards the products. When we have weak acids, it's going to be towards the reactants. for our Ka values. For our strong acids, we're going to have a large Ka. For our weak acids, we'll have a really small Ka. For our strong acids, when we're looking at the amount of ions that form, 100% of the original acid separates and forms these ions. For our weak acids, only a small percent of our original acid separates to form those ions. And when we're looking at our conjugate base strength, strong acids have a very weak conjugate base, but weak acids have a very strong conjugate base. Okay? And then you'll see a very similar relationship with the strong bases versus weak bases. So let's write out an acid dissociation expression for nitrous acid, HNO2. To write out your acid dissociation expression, you're going to first need to write out the reaction of HNO2 with water. And once you have that, then you're going to be able to use that reaction and set up your acid dissociation expression. Okay. But first, you've got to look at your acid in this case and write down what happens when it's reacting with the water. It's a weak acid, so it's going to have the double arrow. Weak acids and weak bases are all going to have the double arrow. And because it's an acid, it's going to be donating its proton to the H2O, forming H3O plus. And its conjugate base, NO2 minus. Okay, and so if we're going to write the acid dissociation expression, which is Ka, that means our products divided by our reactants, but leaving out the liquid water. So we're going to have H3O plus times NO2 minus divided by HNO2. Okay, that's going to be our acid dissociation. So let's take a look at the next part, which is talking about water specifically and what's happening with the dissociation of water. We're going to be able to use what happens with water to help us figure out how acidic or basic a solution is. We're talking about acids and bases here, so we need to be able to figure out how acidic or basic a solution is. So when we have water that's all by itself, you have water molecules that are just reacting with themselves. Water will undergo a process called autoionization, which means that even if it's left alone, it can just form some ions and then reform molecules, right? We see that back and forth reaction here. So H2O plus H2O can produce some H3O plus and some OH minus, all right? That's just what happens with water when it's left alone and it's not reacting with anything. So we have the same reaction written out down here, H2O plus H2O, and it's producing H3O plus and OH minus. But they're kind of showing you here how one of the waters is acting like an acid and it's donating a proton and it's becoming OH minus, which is the conjugate base. And then you have another water that's acting like a base and it's accepting an acid, or it's accepting an H plus rather, it's accepting a proton and it's becoming the conjugate acid here. Okay. When you have pure water that's left on its own, over time, it's going to reach equilibrium and there's going to be a certain amount of each of these ions present, a certain amount of H3O plus and OH minus present. Okay. And we can look at the concentrations of both of these in pure water to give us an idea of what neutral levels of hydrogen ion and hydroxide ion should be. right? We know that pure water is going to be neutral. It's not going to have any acidic or basic tendencies if it's pure water. And if we actually took some pure water and we looked at the concentrations of H3O plus and OH minus, we would see that the concentrations of both of these at 25 degrees Celsius are going to be the same. In pure water, they're both going to have a concentration of 1 times 10 to the negative 7 molar. So in pure water, the concentrations of H3O plus and OH minus are equal to each other, which means that pure water is not acidic or basic. It's exactly in the middle. It's absolutely neutral. And the concentrations of the H3O plus ion and the OH minus ions are exactly the same. Okay. So if we measure these concentrations and we see that each one has a concentration of 1 times 10 to the negative 7, we can write out an equilibrium constant expression for our water. Let's take a look. I'm going to write this on the board so that you could see it kind of come together instead of looking at the finished product on the board. So when we look at our reaction that they've given us here, H2O liquid plus H2O liquid gives us H3O plus and OH minus. And they're telling us that at equilibrium in pure water at 25 degrees Celsius, the concentration of the H3O plus is 1.0 times 10 to the negative 7 molar. And the concentration of the OH minus is 1.0 times 10 to the negative 7 molar. Okay. We know that if this is an equilibrium reaction, that we can write a K expression for it. The K expression we're going to write for this is going to be called KW because it's talking about water and what happens in water. So it's a K value for water, or the water dissociation constant. And when we write out our K expression for this, remember, we only include the aqueous things. We're not going to include the pure liquids. So we have H3O plus times OH minus, right? That's our equilibrium expression for water, our water dissociation constant. And just like we were finding K values for our other reactions at equilibrium, we can find our K value for water at equilibrium. We know that the concentration for H3O plus and the concentration for OH minus are both going to be the same thing. So the KW value for water at 25 degrees Celsius is going to be 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7. Which is going to give us 1.0 times 10 to the negative 14. As long as we're at 25 degrees Celsius. When the temperature changes, that value will change. Okay. But what that means is that as long as we're at this temperature, if we have an acidic or basic solution, we're going to be able to figure out the concentration of H3O plus, for example, as long as we know the concentration of OH minus, because we know that when we multiply these, it's going to equal KW. Right? So if I know the concentration of hydroxide, I can find the concentration of H3O plus. If I know the concentration of H3O plus, I can find the concentration of OH minus. All right. What we also know from this relationship is that whenever these two numbers are the same, whenever they're equal, our solution is going to be considered neutral. All right. So when our H3O plus concentration equals our OH minus concentration, our solution is neutral. Okay. When our H3O plus concentration is bigger than our OH minus, that's when our solution is going to be acidic because we have more of the acid component. And when our OH minus concentration is bigger, our solution is going to be basic. Okay. Let's look at that recap on the slides. Okay, so our dissociation constant for water, or our ion product constant, which is Kw, is going to be the product of the concentrations of H3O plus and OH minus. So when we multiply those things together, and that Kw value is going to be equal to 1.0 times 10 to the negative 14, as long as we're at 25 degrees Celsius. When these two concentrations are equal, our solution is neutral. When our H3O plus concentration is the bigger concentration, then our solution will be acidic. When our hydroxide concentration is the bigger one, then our solution is going to be basic. And as long as we know the concentration of one of these two values, we can find the concentration of the other value. Okay. So we know that Kw equals H3O plus times OH minus, and we know that Kw equals 1 times 10 to the negative 14. So if I want to find my H3O plus, I can take Kw and I can divide it by my hydroxide concentration, as long as I know my hydroxide concentration. If I know my H3O plus concentration and I want to find my hydroxide concentration, I'm going to do Kw divided by my hydrogen concentration. All right. Notice for the H3O plus, this is the hydronium ion. And I know that I've been using this sort of interchangeably with the hydrogen ion throughout the, this video. Those terms are used interchangeably to indicate the acidic part of the solution. So specifically, the H3O plus is technically called the hydronium ion, and the H plus is called your hydrogen ion or your proton. But they mean the same thing. Okay, so that's why for shorthand, I've been referring to this as your hydrogen ion, even though it's H3O plus instead. Our pure water is neutral, and this is when these two values are going to be equal to each other, right? Exact even levels. As soon as one of these gets bigger than the other, that's when the solution turns either acidic or basic, depending on which one's bigger. In our acidic solutions, our H3O plus concentration is going to get larger, and our hydroxide ion has to get smaller as the H3O plus gets larger, because when you multiply these, they still have to equal 1 times 10 to the negative 14. But when our H3O plus is the bigger number, then our solution is acidic. When our hydroxide ion concentration is the bigger value, then our solution is going to be basic. And you're going to see as the hydroxide concentration gets bigger, the H3O plus concentration is going to get small. Okay, those are our little comparisons there. So we can tell whether a solution is acidic, basic, or neutral based on our exponent values here. Okay, when our H3O plus and our OH minus are the same exact number, then we know that solution's neutral. In the second and third examples here, we have 1 times 10 to the negative 2 versus 1 times 10 to the negative 12 for hydroxide. So this is way bigger, so it's acidic. 2.5 times 10 to the negative 5 is way bigger than 4 times 10 to the negative 10. So this is acidic. For our basic solutions, we have 1 times 10 to the negative 8 for our H3O plus versus 1.0 times 10 to the negative 6 for our hydroxide. So our hydroxide's bigger in this case, which is why it's basic. And then for our last example, we have 5 times 10 to the negative 11 versus 2 times 10 to the negative 4. 2 times 10 to the negative 4 is definitely the bigger number. So our hydroxide is bigger in this case. So it's going to be a basic solution. So let's look at an example here. What is the H3O plus concentration of the solution if our OH minus is 5.0 times 10 to the negative 8 molar? Okay. And so for this, you can talk yourself through it because you know that your H3O plus times your OH minus equals KW. And so if we're trying to find H3O plus, then we're just going to divide both sides by OH minus. And now we see that our H3O plus is going to be equal to KW divided by OH minus. And the other values that we know that KW is going to be 1.0 times 10 to the negative 14. And we know in this case that our OH minus concentration is 5.0 times 10 to the negative 8 molar. So that's what we're going to plug in over here. Okay. And we're going to get 2 times 10 to the negative 7 molar as our H3O plus concentration. The other thing that they could ask you here is whether the solution would be considered acidic or basic based on this information. So you would have to look at the value for your OH minus and the value for your H3O plus. You'll see that your H3O plus value is the larger of the two values. And so you know that this solution is acidic. It's always good to practice that part of it when you're doing these calculation type questions. All right, let's look at the next question. Okay, so here they're asking us if lemon juice has an H3O plus concentration of 2.0 times 10 to the negative 3, what is the hydroxide concentration of the solution? And we are going to see something very similar for answering this question, because H3O plus times OH minus is still going to be KW. So this time we're trying to find hydroxide, so we're going to divide both sides by H3O plus. Okay, so to find our hydroxide concentration, it's going to be KW, which is 1.0 times 10 to the negative 14, divided by our H3O plus concentration, which is 2.0 times 10 to the negative 3. And we're going to get 5 times 10 to the negative 12 molar as our concentration for our OH minus. And we see that in this solution, our hydrogen ion concentration is significantly larger than our hydroxide ion concentration. This solution is going to be an acidic solution, which makes sense. It's lemon juice. All right. The next thing we're going to look at is the pH scale. The pH scale is the way that we are going to measure how acidic or basic a solution is. And so we're going to want to be looking at a few of these calculations, like how we calculate the pH and the pOH based on the different values that were provided. Okay. So for the pH scale, for an introduction to our pH scale, it's out of 14. Okay. It goes from values right around 0 to right around 14. You can have values that are a little bit lower than 0 and a little above 14, but that's in very, very concentrated cases. The pH scale is used to indicate how acidic something is. Okay. So the number 7 is going to be the midpoint of our pH scale. Anything that has a pH of 7 is going to be considered neutral. And when something has a pH of 7, its hydrogen ion concentration and its hydroxide ion concentration will both be 1 times 10 to the negative 7. When something is acidic, it's going to have a pH value below 7. Okay, below 7. So the lower the number is on the pH scale, the more acidic that substance is. Something is basic when it has a pH value above 7. So the higher the number is, the more basic the substance is. And we're going to see that our pH values are going to have an inverse relationship to our H3O plus values, because our H3O plus values, as they get bigger, as they get larger than 1 times 10 to the negative 7, the pH values are going to get smaller. They're going to fall below 7. Okay. And for our bases, as our H3O plus values fall below 1 times 10 to the negative 7, meaning they're getting less concentrated, our pH numbers are going to go above 7. They're going to fall into that basic range, which are numbers that are greater than 7. Okay. Let's write a little summary of that for our pH scale. Okay, so we go from 0, and then we're going to have 7, and then we're going to go up to 14. Okay, so everything over here is going to be acidic. Everything here is going to be basic. This is neutral. So when we're acidic, we're going to have pH values below 7. And we're going to have H3O plus values above, greater than 1 times 10 to the negative 7. When we have basic solutions, we're going to have pH values above 7, all the way up to 14. And for our basic solutions, we're going to have H3O plus values less than 1 times 10 to the negative 7. Okay. That's our breakdown of that scale. Now we can use different, we have different methods to measure pHs. We want to look at a few of those. Let me bring up the slide for that. There are what are called pH meters, which is what you have here, where you can put the electrode into a solution and you'll get a pH reading back from that. You have different types of pH papers. This is a type of pH paper that you could use. The pH papers you can dip into a solution and they'll turn a particular color based on how strong the acid or base is. Some pH papers can give you colors that are specific to a particular value of pH. Okay, so in this case, we're looking at something that has this orangish color, so maybe a pH of 3 or 4 in this case. All right. You also have indicators that turn different colors based on their pHs. So you can have a solution and you can compare it to a known indicator to figure out its pH, or you can add an indicator to it and see what color it turns. Like we said, for our pH scale, values below 7 are acidic, neutral is going to be 7 exactly, and above 7 is basic. And these are some common substances and where they fall on our pH scale. So neutral is going to be about 7. You'll see that even our drinking water is a little above 7. A lot of cleaners are basic, so they're going to be above 7. But a lot of juices and sodas and things are in the more acidic range. So we want to look at this list and based on the information that they give us, decide whether it's acidic, basic, or neutral. So think about the little distinction that we made on the board, okay? HCl with a pH of 1.5. If the pH is 1.5, that means that it's a pH below 7, which means it's going to be acidic. We have pancreatic fluid, where your hydrogen ion concentration is 1 times 10 to the negative 8. So you have to ask yourself, is that number a bigger number or a smaller number than 1 times 10 to the negative 7? That's a smaller number than 1 times 10 to the negative 7, which means that this is going to be basic. Okay. Sprite soft drink, pH is 3. Again, that pH value is below 7, so it's going to be acidic. When your pH is 7, that is the definition of neutral. When your hydroxide ion concentration is 3 times 10 to the negative 10, that's a tougher one because now you have to say, well, what does that mean for my hydrogen ion concentration? So what you can do is do your calculation for using your Kw value. We know that H3O plus is going to equal Kw divided by OH minus. So if you have a Kw of 1 times 10 to the negative 14 divided by a hydroxide concentration of 3 times 10 to the negative 10, you are going to have a hydrogen concentration of 3.3 times 10 to the negative 5. And now it's a lot easier to look at this and say, well, this is my hydrogen concentration. This is my hydroxide concentration. This one's bigger, so this is going to be acidic. Right? Whenever your hydrogen, your H3O plus concentration is bigger than your OH minus concentration, then your solution is going to be acidic. So this one is also going to be acidic. That was neutral, acidic, basic, and acidic. And then for our last one, our H3O plus is 5 times 10 to the negative 12. That number is definitely smaller than 1 times 10 to the negative 7. So this is going to indicate a basic solution as well. Okay. Now we want to be able to measure our pH. We want to measure the acidity. And so there is a formula that is going to allow us to find the pH as long as we know our H3O plus concentration. Or if we know our pH, we can find our H3O plus concentration from the pH. This is the part of the class where if you do not have a scientific calculator, you're going to have to correct that. You need to have a scientific calculator that has a log function to it in order to find your pH values and to find your hydrogen concentration values from the pHs. Okay. These two calculations are sort of opposite functions. If you look at the log key on your calculator, you'll notice that every calculator where it says log, there's going to be something written right above the log, and it's going to be 10 raised to the x. So that's because the sort of the opposite function of log is going to be the 10 raised to the x, because these are all log base 10 when there's no number written down there. So when we are finding the pH of something, we're going to take the negative log of that thing. Remember how I said we use the hydrogen ion and the H3O plus, and we kind of use them interchangeably? When we find the pH of something, that little p, that stands for the negative log. And what we're taking the negative log of is our hydrogen ion concentration, which is this part here. Okay, so we're taking the negative log of our hydrogen ion concentration. That's what pH means. When we want to find our hydrogen ion concentration, we're going to take that log function and we're going to use its opposite. So we're going to do 10, and then we're going to raise the negative pH, 10 to the negative pH, to find our H3O plus concentration. Okay, those are our related formulas here. So let's look at this in action a little bit. What we're going to see is that the lower our pH value is, the more acidic our solution is. The higher our pH is, the more basic our solution is. You'll also see that every 1 pH unit is going to correspond to a factor of 10 in terms of the acidity. Okay, the normal pH range is 0 to 14. pH of 0 is something that has a H3O plus concentration of 1 molar. We're going to see that something that has a pH of 14 is going to have a hydroxide ion concentration of around 1 molar. And the only time we're going to see pHs that are out of the range of 0 to 14 is when we have something that is extremely concentrated, very acidic. If it's above 14, it's going to be extremely concentrated, very basic. All right. And when we're doing our pH calculations, we are going to figure out how many significant figures and decimal places there are based on this relationship here. When we are taking the negative log of the hydrogen ion concentration, we're going to count the number of significant figures in that hydrogen ion concentration. And however many significant figures are present, that's how many decimal places we're going to include in our pH. So if we have a concentration with 2 significant figures, then our pH is going to have 2 decimal places in it. Okay. So we have a few calculations that we're going to look at. Our first one here, they have aspirin, which is acetylsalicylic acid, was the first non-steroidal anti-inflammatory drug used to alleviate pain and fever. If a solution of aspirin has an H3O plus concentration of 1.7 times 10 to the negative 3 molar, what is the pH of the solution? And so for this one, we're going to start by writing out our formula. pH equals the negative log of our H3O plus concentration. And plug in 1.7 times 10 to the negative 3. When you plug this into your calculator, depending on the calculator that you have, this negative sign, you don't have to plug into your calculator necessarily, okay? If you want, you can ignore that for now, and you can just worry about taking the log of this number, okay? Whatever value you get when you take the log of this, you can look at that number in your calculator, and then you can reverse the sign, right? So if you have a calculator like this one that doesn't have, and this is a little more basic, so it's not like you're plugging in all the values here. For me to plug the log into this calculator, I have to I have to type in the number. So 1.7 times 10 to the negative 3. And then I have to hit the log key. And so it gives me negative 2.7695. So once I have that number, I'm going to hit the plus minus key down here. And now it's going to take away the negative. So my pH here, because I have two significant figures, I'm going to keep two decimal places. And my pH is going to be 2.77. Okay. Let me find another calculator real quick. I'm going to pause this real quick just to get one of the other calculators out here. All right. So for a calculator like this one, this is the TI-30X2S. For this one, you'd want to hit the log key first. And when you hit it, it's going to say log, and then there's going to be a place for you to input the number. So it'll have a parentheses and a place for you to input the number. So now we're going to put in the 1.7. I'm a fan of using the scientific notation key, which is that double E right there. So I'm going to hit second and then the double E, and then put in my negative 3 exponent. And then I'm going to close my parentheses. So just so you see what that looks like in there. So it says log out front and then 1.7 E negative 3. Then we hit our equals and we get negative 2.76955. And so that's when you take away the negative sign and it's 2.77. Okay. All right. We have another couple examples for this one. Let's look at this. I'm just going to put up the questions first so that you can see how they're how they're stated. But what we're going to write down is the number that they're giving us. So here they're telling us that H3O plus equals 4 times 10 to the negative 5. I very strongly recommend that for each of these that we're doing right now, that you pause and you try to put this in your calculator before I do. Okay. And I'm going to just put up the question that follows this so that we can do both of these. So this is question 2. And then question 3 is find the H3O plus concentration. For a solution with a pH of 3.42. So for our first one, we're going to find the pH from this. And pH is going to be the negative log of our H3O plus concentration. So it's going to be the negative log of 4.0 times 10 to the negative 5. Okay. So again, for this calculator, 4 times 10 to the negative 5, and then I'm going to hit my log key, and I get negative 4.3979. So I'm going to make that positive. I want to keep two decimal places because I have two significant figures here. So my pH is going to be 4.40. Okay. Now for our next question, they're giving us the pH and they want us to find H3O plus. So we're going to have to use that other version of the equation that we talked about to find our H3O plus from our pH. It's going to be 10 to the negative pH. Okay. So this is going to be 10 raised up as an exponent negative 3.42. Okay. If you have a calculator like this one, the way that I have to plug this in is 3.42 and make it negative. And then I have to hit my second key. So 3.40, negative 3.42 is in there. Then I'm gonna hit the second key and then the log key, because right above the log key is 10 to the X. And that's what I want here. So second log. I'm going to get a number with a lot of decimal places. So I'm going to hit the second key and the number 5 to turn it into scientific notation. And it tells me that it's 3.8 times 10 to the negative 4 molar. Okay. If you got a calculator like this one, you can put this in a little more, I guess, logically. You can do the 10, the second key, and then hit log, and you'll see that it brings up a 10 with a little caret and then a parentheses, and it's just waiting for you to put in the number. So then you can put in negative 3.42. And again, you're going to get that same decimal back out. Okay. This you can also put into scientific notation key. If you're still not sure how to do that, you can come up and ask me, but you're still going to get the same 3.80 times 10 to the negative 4 as your answer. We're only going to keep 2 significant figures though, because we only have 2 decimal places here in the pH. That's why we're only keeping 2 significant figures here. Okay. All right. Let's look at something that's related to the pH scale, but it's on the opposite side of it. And this is going to be called, this is like the alternate scale. This is going to be our pOH scale. And where our pH measures the acidity of a solution, the pOH scale measures the basicity of a solution, how basic something is. And when you're on the pOH scale, it works the same way that the pH scale worked for acids. On the pOH scale, things that are very close to 0 are very basic. Things that are at a pOH of 7, this should say pOH, is neutral. And when things are acidic on the pOH scale, they're going to have a pOH that's greater than 7. So it's the exact opposite of our pH scale. Okay. And that should make sense to you because look at what's here. There's not a hydrogen after the P, there's a hydroxide. So when you're finding the pOH, you're taking the negative log of your hydroxide ion concentration, not your hydrogen ion concentration. Okay. The formulas look dead similar though. To find the pOH from the hydroxide ion concentration, it's just going to be the negative log of your hydroxide ion. To find the hydroxide ion concentration from your pOH, it's going to be 10 raised up to the negative pOH. So the formulas look exactly identical as to our pH scale, but with our pH scale, we're using our H plus concentration. And for our pOH scale, we're using our OH minus concentration. The pH scale and the pOH scale are related to each other because when something has, when you know something's pH, you can automatically find its pOH because the pH of something added to its pOH will always add up to 14. So for example, in this example that we looked at here, if I know that something has a pH of 3.42, I can automatically find its pOH by doing 14 minus 3.42. So its pOH is going to be 10.58. Okay? Because pH plus pOH will always equal 14. So our pOH scale is just going to be the opposite of our pH scale. I think these are all repeated repetitions of what we've already said. What's important to really take away from this, though, is that if you know the pH, you can already find the pOH. Like you know it already. You just have to do a subtraction. If you know the pOH, you can automatically find the pH. You just have to do a subtraction. So let's look at this example. Find the pH of a solution that has a pOH of 2.96. So we know that pH plus pOH is 14. So if I want to find the pH, it's going to be 14 minus pOH, which will be 14 minus 2.96 in this case. So that's going to be a pH of 11.04. The next question is, how do you find the pOH of something, of a solution that has an H3O plus concentration of 7.2 times 10 to the negative 9? There's a few ways you can do this. I'm just going to show you one of them. Well, maybe I'll show you two. So if this is the information that we're given and we want to find the pOH, there's two different pathways you really can take here that will both lead you to the same place. You can either take this information and you can find the hydroxide ion concentration and then find the pOH. That's a perfectly valid way to do this. Or you could take this information and you can find the pH and then find the pOH. Okay. So let's say that we want to do this first method and we want to take our H3O plus and we're going to find the OH minus from that. We're going to remember that KW equals H3O plus times OH minus. So if I want to find OH minus, my OH minus is going to be KW divided by H3O plus. Okay. So my OH minus is going to be 1 times 10 to the negative 14 divided by 7.2 times 10 to the negative 9. My hydroxide ion concentration is going to be 1.39 times 10 to the negative 6. And so now if I want to find my pOH, it's going to be the negative log of my hydroxide ion concentration. So that's going to be the negative log of 1.39 times 10 to the negative 6. This is only the two significant figures. I'm just keeping an extra one for my calculation right now. So I'm going to take the negative log of this number and I'm going to get 5.86, which I'm going to round to 5.9 because I have two significant figures. Oh no, two significant figures here means two decimal places for my pH. So 5.86. Okay. That's my pOH using this method. For my second method, first I'll find my pH. So my pH is going to be negative log of my H3O plus. So it's going to be negative log of 7.2 times 10 to the negative 9. So that's going to be 8.14. And then step 2, to find my pOH, I'm going to remember that pH plus pOH equals 14. And so my pOH is going to be 14 minus 8.14, which is 5.86. So either of those methods are perfectly valid to answer that question. Okay. All right, so we're going to look at some reactions next. Now that we've learned what our acids and bases are, we actually want to look at some of the acid-base reactions that are happening here. A lot of this is going to seem familiar to you because we've looked at a lot of these types of reactions already. We're just seeing them in a different context now. So when you have reactions with acids, you're going to see a few different common themes emerge from acid reactions. When acids react with metals, they're going to form a salt and they're going to form hydrogen gas as a product. When acids react with bases, this would be considered a neutralization reaction that will form salt and water. And when acids react with either a bicarbonate or carbonate ion, it's going to produce some carbon dioxide gas. When we say that a salt is produced, we're talking about any ionic compound that does not have hydrogen as the cation or a hydroxide ion as the anion. So things like sodium chloride or potassium nitrate, things that are ionic but don't contain either of these ions. That's what is meant by salt in this context. So when we're looking at our reactions with acids and metals, here you see magnesium and hydrochloric acid. The salt is the MgCl2, and then hydrogen gas is produced. When zinc and hydrochloric acid react, our ZnCl2 is the salt, and the hydrogen gas is also produced. When we have our carbonate and our bicarbonate reaction, our acids will react with either the carbonate or the bicarbonate, and they're going to produce CO2 gas. They're also going to produce water. And then the salt that's produced is going to be a combination of the cation that was present in the carbonate or the bicarbonate and the anion that's present in the acid. So for our first example, we end up with calcium chloride because here's the calcium and here's the chloride. For our second example, we ended up with NaCl as our salt because our sodium was in the bicarbonate and the chloride was in the acid. And in our neutralization reactions, we're going to have an acid and a base that are present. They're going to combine. The hydroxide and the hydrogen are going to form water. And then in this case, the sodium and the chloride that are left over are going to form the salt. Okay. For any neutralization reaction, when we are looking at a strong acid and a strong base, we're going to see that the same net ionic equation will always occur from any strong acid, strong base reaction. And you remember the process of finding our net ionic equation. We look at our overall reaction. We break up all of the aqueous components into their individual ions. And then we eliminate the spectator ions. And in that case, what's left when we eliminate our spectator ions is H plus OH minus produces liquid water. And this is going to be our net ionic equation. And this is always the net ionic equation for any strong acid, strong base reaction. When you're balancing any neutralization reaction, you're going to first write out your reactants and products. And you can sort of shortcut your balancing by using a comparison between the hydrogens in your acid that are present and the hydroxides in your base that are present. Because these numbers have to be the same. You have to have the same number of hydrogens in your acid as there are hydroxides in your base. Once those numbers are the same, you're going to be able to balance out your water molecules to make them match up how many hydrogens and hydroxides you have. And then whatever salt forms you can write from the ions that are left. Okay. So for an example, you have magnesium hydroxide and HBr. So what they're suggesting here is that you look at the fact that you have two hydroxides and you have one hydrogen here. And so you're going to need two hydrogens to match your two hydroxides. And if you have two hydrogens and two hydroxides, that means that those are going to combine to make two H2Os. I don't know why I'm writing this on here instead of writing it on the board. I just write this on the board. Just messy otherwise. But that's like the process. I just kind of wanted to show you the process that they were talking you through. You could go through and you know enough at this point to actually just write out the products of this reaction and balance it. What they're giving you here is a type of shorthand that you can use. So when you see that there are two hydroxides present and there's only one hydrogen, you know that these two things have to be the same. And when you have two hydrogen ions and two hydroxide ions present, those are going to combine and they're going to make two waters. Okay. What you have left after those combine, you're going to have a magnesium ion, which is Mg2 plus, and you're going to have two bromide ions. Each one is going to be Br minus 1. So when these two things combine, you're going to end up with Mg Br2. And that will be aqueous because bromide ions are soluble and magnesium is not an exception. Okay. So they're asking us in the next example to look at two reactions and pick out the correct set of coefficients that will balance them. And again, the way that we can do this is kind of look at those steps that they gave us and figure out like, all right, we know the things that have to match now. For our first example here, we know that the number of hydroxides that are present here have to match the number of hydrogen ions that are present here. So this has to be a 3 out in front. And if I have 3 hydrogens and I have 3 hydroxides, then I have to have 3 waters. Have to. And so right away, you can get rid of this answer choice. That's no good. For this one, the 3 is okay. The 1 is okay. This 1 is okay. But this 3, that one's no good. This is the one that's correct. For our second example, we've got barium hydroxides. We've got 2 OHs here, and we have H3PO4. So we have 3 hydrogens here. We have to have the same number of each. So the way that you're going to make something that has a 2 and something that has a 3 the same, right? We're going to switch around those numbers. So we're going to put a 3 in front of our barium hydroxide so that we end up with 6 hydroxides overall. And we're going to put a 2 in front of our H3PO4. So we end up with 6 hydrogens overall. Okay. If I have 6 hydroxides and I have 6 hydrogens, that means I'm going to be making 6 waters. Okay. So when I'm looking at my distribution here, I have to have a 3 in front of my barium. So this, no good. I have to have a 2 in front of my H3PO4. Okay. When I look at my barium phosphate, I see that right now I have 3 bariums and I have 2 phosphates, which are what I have on my reactant side. So I don't need to change my coefficient in front of my barium phosphate. It could just stay as a 1. And I've got 6 waters. So this is going to be my correct distribution of coefficients in that example. Okay. If that seemed too quick or if it didn't quite make sense, you can absolutely pivot back to the table method that we used for our earlier balancing, and that will 100% still work here. Okay. And do what gets you the correct answer every time. You don't have to do the fastest thing. You just have to do the thing that brings you to the correct result. Let's talk about titrations next. This is another use of the acid-base reactions. Our acid-base titrations are when we're going to have a volume of acid, um, known acid, or a known volume rather of acid, that we place in a flask, and we'll put some indicator in this flask. So right now you see how this is the acid that's in here, and the acid it's transparent, right? You can't see anything in there. Right now your acid's in here and your indicator is in here, and neither of them have a color. In your burette up here, this is your base. In this case, sodium hydroxide. And when we're doing a titration, we're going to be adding the base from the burette into the flask that has our acid. And notice how, as these slides progress, that volume gets lower and lower and lower because we're adding more and more base to our acid. And the purpose of a titration is to use a color change to help you figure out when the amount of acid that's in your flask is the exact same amount of acid or the same amount of base that you've added from your burette, when those two amounts of acid and base are the same. Okay. When the amount of acid that you have present in your flask is equal to the amount of base that you've added, you have neutralized your solution and you'll be at your titration's endpoint. The endpoint of your titration is something that you'll be able to visually see as a color change, because your solution will go from completely clear, and then as it starts to neutralize, you'll start to see this like pink color, for example. And then as soon as the whole solution turns that very light pink, you'll know that you have reached the point where your solution's neutral and your amount of acid and your base they're going to be equal to each other. Okay. So in a titration, we use this in lab to figure out the molarity of an unknown acid. We use a base like sodium hydroxide in order to neutralize our measured volume of acid. We'll add a few drops of an indicator like our phenolphthalein to our acid to help us visually identify our endpoint. Okay. And we just keep track. So we keep track of that acid solution. We know exactly how much we added at the beginning, and we watch and we see how much base we add. And at the point where our solution turns pink, we'll stop adding the base and we'll look and we'll see what volume of base we've added. We know the molarity of the base that we were using. So we'll be able to figure out how many moles of base that we needed to add to our acid solution in order for it to be completely neutralized. Okay. Our indicator, like phenolphthalein, is what's going to allow us to make this judgment, because when it turns pink, then we'll know that the moles of our acid and the moles of our base are equal to each other. It's going to just look clear before that. All right. Our endpoint of our titration is when this color change happens. And at our endpoint, we're going to see that pink color, and then we're going to know that the moles of our base that we've added are equal to the moles of the acid that are already in our solution. Okay. And if we know the moles of the acid that are present, and we know the volume of the acid that we added originally, we'll be able to calculate the molarity of our unknown acid, because we know that molarity equals moles divided by liters. Okay. So as an example, let's take a look at this. What's the molarity of an HCl solution if 18.5 milliliters of 0.225 molar sodium hydroxide is required to neutralize 0.0100 liters of HCl? All right. I know that seems like a lot when you're just looking at it, but when we treat this like any other reaction that we've looked at, same number of steps, it makes sense, I promise. So you write down your reaction, and then you're going to write down the information that they give you about each part of this reaction. Okay, so this is just a neutralization reaction. Acid plus base gives us our salt plus our water. We don't care about the product part here. We're going to focus in on our reactants. They're telling us that we added 18.5 milliliters of 0.225 molar sodium hydroxide to neutralize 0.0100 liters of HCl. Okay, and our goal is to find capital M, find the molarity of our HCl. So when you look at the information that you're given, just like with what we looked at with our reactions previously, we can identify the thing that we know the most information about. It's our NaOH. We have the molarity and we have the volume here. So the first thing that we can do is find the moles of our NaOH. Okay. Once we have the moles of the NaOH, make a list right here. Step 1, find our moles of NaOH. Step 2, use the moles of NaOH to find our moles of HCl. And once we know the moles of HCl, we can find the molarity of HCl. All right. So how do we find the moles of the NaOH? Molarity times volume in liters. All right, so I've got a molarity of 0.225 molar. My volume here, I'm going to convert this into liters by dividing it by 1,000. So that when I do my multiplication, it's already in terms of liters. Okay, now I'd recommend looking back at your neutralization reaction at this point. You have to make sure that your mole coefficients are being taken into account in step 2. The only way that you can switch from one reactant to another reactant is through your balanced equation. Now here, we have a 1 mole to 1 mole ratio. Okay, so our moles of NaOH are going to be exactly equal to our moles of HCl. But we can prove that using our balanced equation. Our moles of HCl, to find those, we're going to take our moles of NaOH and we're going to say that according to our balanced equation, every 1 mole of NaOH is going to react with 1 mole of HCl. So if I added 0.00416 moles of NaOH to reach the endpoint, to reach that point where I've neutralized everything, that means that I must have only had 0.00416 moles of HCl present. And once I know my moles of HCl, I can find my molarity of HCl because it's going to be moles divided by liters. So I'm going to take my 0.00416 moles of HCl and divide it by my volume in liters that they gave us, 0.0100 liters. And we're going to end up with a molarity of 0.416 molar. That's the concentration of our HCl. Okay. Let's share the screen one more time. Write down the second example here. Same reaction. We're still using our HCl reaction and our NaOH, but they've given us different values to work with. Here they're telling us that we have 0.0250 liters of HCl, and we have 25.5 milliliters of 0.438 molar NaOH. Okay. But the reaction's the same. So we're going to be able to reference our first reaction when we answer this question. Okay. You're going to see that even though the numbers in the question have changed, our steps aren't going to change. We still have to find our moles of NaOH first. We still have to relate it to the moles of HCl in our second step. And then we have to use that information to find the molarity for HCl. Okay. So we're going to take our volume of NaOH they've given us here and turn it into liters. And then we're going to find our moles of NaOH first. So step one, moles of NaOH. And that's going to be our molarity of NaOH, which is 0.438 times that volume in liters, 0.0255. And we end up with 0.0112 moles of NaOH. Okay. Step two, I'm going to find my moles of HCl because I'm going to take my moles of NaOH and I'm going to look at the mole ratio between my HCl and my NaOH. Every 1 mole of NaOH that reacts is going to use up 1 mole of HCl. So if I have 0.0112 moles of NaOH, I've got 0.0112 moles of HCl. And step three, I'm going to find my molarity of HCl by taking my moles of HCl and dividing it by the liters of HCl that they gave me in the question. And we end up with a molarity of 0.448 molar. Okay. So like I said, I mean, it works the same way as all of the other stoichiometry and reactions that we've already worked with. Okay. It's just this time we're looking at acids and bases. All right, we have one more part of this chapter to look at, and that's going to cover buffers. Let's go back to the slides and look at what we're talking about with the term buffers. We use the word buffer like in our daily lives a lot. And in terms of chemistry, it kind of means the same thing. A buffer is something that is going to act as like almost like a little bit of a stopper to prevent really drastic change from happening. Okay. So when you have a buffer solution, you can add acid or base to that buffer solution. And we're not going to see a very big pH change. If you add an acid or a base to water, you'll see a very big pH, either a drop if you add an acid or an increase if you add a base. Like if it goes from neutral water that's at 7, you add some acid, it might drop 3 down to 4. If you have a buffer solution that starts off at like this, in this particular buffer, it's starting off at 7. Buffers can start off at different pHs. But when you have a buffer solution and then you add acid to it, look at the difference in that pH change. Instead of dropping all the way down to 4, it only dropped down to 6.9. When we took the buffer and we added OH minus to it, it only increased to 7.1. It didn't jump all the way up to 10.5. So buffers are present to make sure that very large changes in pH don't happen during your reaction. Okay, they're supposed to kind of maintain a steady pH. Your buffers are going to work because they are made of weak acid and weak base components that are able to like absorb hydrogen ions or absorb hydroxide ions, depending on what's being added. In that way, they resist pH changes because they're using up the acid and the base that gets added to the system. We have a lot of buffers in our body systems. They maintain proper functioning of our cells in our blood. Our pH, our blood has a pH that's real close to 7.4. And the way that that blood pH is able to stay maintained is because of buffer systems that work to keep the blood pH right in this range. Buffer solutions are going to be created by combinations of our acid-base conjugate pairs. Okay, so any of our weak acid conjugate base pairs or vice versa, like in this case, we have acetic acid and the acetate ion. These will make a very good buffer system. An excellent buffer is going to have equal concentrations of the weak acid and its conjugate base or its salt present. Okay. You want to have as much weak acid as conjugate base so that your buffer is equally good at absorbing either the addition of acid or addition of base to the system. So you're seeing here a buffer with acetic acid and sodium acetate. This is the actual salt that is going to provide our acetate ion. Our sodium acetate, when it splits up into solution, it forms the acetate ion and the sodium ion. The sodium ion we don't worry about because the sodium ion is neutral, but this acetate ion acts as the conjugate base to acetic acid. So when you have a buffer solution, you can have acetic acid present and you can have the acetate ion present from the sodium acetate. And now if you add some strong base to the solution, your acetic acid will work on reacting with that strong base and making sure that the pH doesn't change. If you add a bunch of like HCl to the solution, your acetate ion will work on reacting with the HCl and making sure that the pH doesn't change. Okay, so that's how your buffer is going to work. When you have a weak acid in a buffer, the weak acid is going to try to combine with any base that's added. And as it combines with a base that's added, the weak acid itself gets used up and it forms more of the conjugate base. So you see here, like in this case, we started out with a weak acid and the conjugate base. We added a little bit of hydroxide. And so the amount of weak acid we had went down. And the amount of the C2H3O2 minus we have increased. Because as the acetic acid uses up the hydroxide, it forms more of that acetate ion. Okay. It works the exact opposite way if we are looking at our conjugate base that's in a buffer. Because our conjugate base, which is our C2H3O2 minus, it's going to be able to react with any H3O plus ion that's added. And when these two things react, they're going to form some acetic acid and some water. So as we add acid to our mixture, our buffer mixture, our concentration of C2H3O2 minus, our acetate ion, is going to get smaller, but our concentration of acetic acid is going to get larger. So this is just another visualization of how your buffers are going to work. They start out equal. When you add acid to your buffer, the basic part of your buffer gets used up and more of the acid part forms. On the other hand, if you have your buffer and you add a base to it, the acidic part of your buffer gets used up and more of the basic part is going to form. And your buffer will keep working as long as both components are present. At some point, if you use up one of these components, then your buffer will not work anymore. And then you'll start to see the more drastic pH changes that you would expect from a solution that is not a buffer. Now, if you want to calculate the pH of a buffer, you have to know a few pieces of information. Okay. You have to know the acid dissociation constant of the weak acid that's part of your buffer. And you have to know the concentration of the weak acid and the conjugate base that you're starting with. Okay. With those pieces of information, you can find the H3O plus concentration. And just like we did before, once you know the H3O plus concentration, then you can find the pH because you'll take the negative log of this value. You cannot take the negative log of your weak acid formula. You cannot take the negative log of your conjugate base concentration. The only thing that you can use to find the pH is the H3O plus concentration specifically. Okay. So we want to take our acid dissociation expression and we're going to solve it for H3O plus. And as long as we know these other three pieces of information, we can solve that expression for H3O plus, and then we can find our pH. All right. So let's take a look at this example. They're giving us the Ka for acetic acid. It's 1.8 times 10 to the negative 5. What's the pH of a buffer prepared if we have 1 molar acetic acid and 1 molar acetate ion? Okay. So the first thing we want to do is we want to write down our expression for finding our H3O plus. To find our H3O plus, which we need to find the pH, that's going to be the Ka times the concentration of our weak acid divided by the concentration of our conjugate base. And in our example that they've given us here, our weak acid is going to be our acetic acid. And our conjugate base is going to be the acetate ion. All right. So to find our hydrogen ion concentration, it's going to be 1.8 times 10 to the negative 5 times 1.0 over 1.0. Okay, because both of them were 1 molar. So in this case, our hydrogen ion concentration is just going to be 1.8 times 10 to the negative 5 molar. That's not the pH though. Okay, our pH is going to be the negative log of our H3O plus. So it's going to be the negative log of 1.8 times 10 to the negative 5. So the pH of this buffer is 4.74. Yeah. Okay, 4.74. All right. So that's how we can calculate the numerical pH of our buffer. Let's look at a few more points about our buffer system. Because our Ka is always going to be constant at a given temperature, we can figure out our hydrogen ion concentration by looking at that weak acid to a conjugate base ratio. When we add really small amounts of either acid or base to our mixture, this ratio is only going to change a little bit. And so changes in our hydrogen ion concentration are going to be small changes. And so our pH changes will be really tiny. And so our pH will be pretty steady. But when we add really large amounts of acid and base to a buffering system, this might go past the amount of weak acid and conjugate base that we have. This would exceed the buffering capacity of our system. The buffering capacity, that's referring to the limits of our buffer system. If we pass the capacity, then our system can no longer buffer. Okay. Buffers can be prepared from conjugate acid base pairs. So we've been recognizing conjugate acid and base pairs already. These are acceptable versions of conjugate acid base pairs. I think that's just want you to like pick some out. You want to make sure that if you're being asked like if a pair of if a potential pair of substances is a good buffer pair, you have to make sure that they're conjugate acid base pair of some sort. You can't have two random things next to each other. Each of these components are related to each other by the addition or removal of an H plus. Okay, that's what makes a good conjugate acid base pair, a good buffer pair. Here they're giving us another example of finding the pH. So using a common phosphate buffer for biological specimens, find the pH of a buffer if we have 0.775 molar H2PO4 minus and 0.625 molar HPO4 2 minus. Okay. The more positive one would be considered our weak acid. The more negative one would be considered our conjugate base. Okay. And they're giving us the Ka for our more positive one. This would be considered the weak acid in the pair. Our Ka is 6.2 times 10 to the negative 8. So notice that the first thing that we do here, we write out that equation for our H3O plus. H3O plus is going to be Ka times the concentration of the weak acid divided by the concentration of the weak base. Okay. Plug those numbers in. I thought maybe I had written out the stuff on the slide. But it's better if we write it out here anyway. So our weak acid in this case is going to be H2PO4 minus, and our conjugate base is going to be HPO4 2 minus. Our acid is more positive, our base is more negative. That's going to be a helpful way for you to recognize which is which. So when we plug this in to find our H3O plus, it's going to be Ka 6.2 times 10 to the negative 8 times, you can put these in parentheses if you want, you don't have to. But the concentration of the H2PO4 minus was going to be 0.775. And the concentration of the HPO4 2 minus is 0.625. Okay. So 0.2 times 10 to the negative 8 times. And we end up with 7.7 times 10 to the negative 8. That's going to be our hydrogen ion concentration. From there, we're going to find our pH. Negative log of 7.7 times 10 to the negative 8. Uh, 7.11. That's our pH here. Let's look at our last example that they're giving us here. Just want you to see the question, and then we can fill it in. We can do it right underneath the last one because it's so similar. It says find the pH of an ammonium buffer. We have 0.778 molar NH4Cl. We have 0.705 molar NH3. The Ka of NH4 plus is 5.6 times 10 to the negative 10. Okay, so let's look at that information that they've given us. They're telling us that we have 0.788 molar NH4Cl. What happens when NH4Cl is in solution? It's going to break up into NH4 plus and Cl minus. This part right here, this is going to be our conjugate acid or our weak acid. Our NH3, we have 0.705 NH3. This is going to be our weak base. Okay, so in this case, they gave us the NH4Cl. They gave us our weak acid as part of a salt. But you still want to be able to look at this and recognize that when you put NH4Cl into water, it's going to break apart into these two ions. And the conjugate acid base pair in your buffer is going to be NH3 and NH4 plus. The NH3 comes from here. The NH4 plus comes from here. Okay. They also tell us the Ka of the NH4 plus, which we need to figure out our H3O plus. So to figure out our H3O plus here, we're going to take our Ka value that they gave us, 5.6 times 10 to the negative 10. And we're going to multiply that by our weak acid concentration. So that's going to be our NH4 plus concentration, 0.778, or 788 rather, divided by our base concentration, which is our 0.705. And we get 6.3 times 10 to the negative 10 as our H3O plus concentration. So now to find our pH, it's going to be the negative log of our H3O plus concentration which is going to be 9.20. So this is going to be the pH of our ammonium buffer system. Okay. And that is it on buffers. And that is it on chapter 11.